arms as the entire kind of code runs.
Yeah, so this is the result. You see that? How all of them are on that right side. Except for like these, but these came back. So this one actually came back as the correct result, and it has more in the lungs, right? So this one, so everything past this should be class normal. Oh wait, no, never mind. Hold on. Everything past, so normal, yada yada. Yeah. So you can see it's all on the right side. I mean, these results are kind of like just useless at this point. But the thing is, it got a really good score on the test set. So if you go up here, it got a decent score on the test set of like 80-something%, right? Yeah, 83% on the validation set. But it's, if you just go by the validation set and you aren't like looking at overfitting, you could, deploy a model that's just checks to see what the shape of the arms of the patient is, not whether or not they actually have pneumonia. But yeah. Gabe, you want to go over the code a little bit?
Yeah, there's a question.
Oh yes.
If you crop the image to not include like the bend of the arm, would it have a better accuracy?
Yeah, but how do we know where to crop the image? So we know that all the data we need is in the image already, right? But how do we figure out where to crop that image so the arm's not in there?
Another network to
That's actually, I've come across that problem many times in terms of image classification and computer vision. And the best you can do is come up with a heuristic. So like if you want to say cut off the arms from the image, just reduce the image, like cut off those image by like, I don't know, 20 pixels. And it's not going to be the same for everyone. But, that's as good as you're going to get.
Yeah.
At least without doing a lot of things like you don't want to use AI.
Yeah.
Can you just determine it by the torso? So like where the black changes to white, and then that would be like the cutoff.
You could.
Yeah.
I've done like edge detection methods for transforming images or filtering images.
But then you also run into the problem. But then you also run into the problem where all the images are different sizes, so you don't have like a set number of things for the actual prediction. Does that make sense?
Yeah.
Okay. Yeah, but that's a good question. I mean, that you could do that, and in general, you want to take the data set you originally have and change it as little as possible, because then that's the best representation of the data that you're ever gonna get is that original data. Yes.
One thing when they're taking medical images now, like X-ray, CT, whatever. A lot of them now are introducing like a radiopaque kind of boundary of where you want to focus your image at. So like what you were talking about with the edge detection, they would provide images with that like already boxed area where you want to be. So it would just be really quick to cut everything else off outside of that box. But a lot of the images you will get right now don't have as clear as data, so you just kind of have to go with it as it comes.
Yeah, and in actuality, the best solution is to just change some hyperparameters and make sure that you're not overfitting, you're not going over too many boxes.
Next week.
So, by the way, next week we have a professor from UF actually talking about how to do that. She's a really good professor.
There's another angle of this that I think is important to explore. Do you have like the accuracy printout? Like in the notebook.
Yeah, I have this one. Or do you want the other one?
Yeah, like in the notebook where you printed out, the accuracy is about 80%.
Oh, yeah.
Yeah, you know what I mean.
Here?
Yes, exactly. Okay, so you see like the validation accuracy is pretty high, and you might think like, oh, the model's about 83, 84% accuracy, this must be pretty good. Well, let's consider the problem of, like you go into the hospital, right, and 90% of patients are fine, right? 90% of patients don't have disease A, and 10% of patients do. And let's say I, as a doctor, just predict that every single patient is normal. What's my accuracy?
90%. Sorry.
Kyle, how'd you figure that out?
Sorry, my bad.
Yeah, so the accuracy is 90%, right? Even though I'm not doing anything, like I'm not considering any of the patient's like data at all. And if I just guess 90%, guess the patient is always normal, I get an accuracy of 90% without doing anything and while being completely wrong. This is a terrible model. And the reason for this is that the data is highly skewed. Most people don't have the disease, and a small number of people do have the disease. But it's really important that when someone has a disease, that we get it right. So this is known as like unbalanced classes, skew, and other names. And when there's skew or unbalanced classes, it's pretty common to have very high accuracy, but actually a terrible model.
Yeah.
So accuracy is actually not the best metric to use in this case.
Yeah.
There's another metric known as F1 score that you can probably look into if you're interested in what to do there. But
Yeah.
Unbalanced classes are really common in medical imaging because like the number of patients who have cancer is going to be much, much smaller than the number of patients who don't have cancer. But it's really, really important that when a patient does have cancer, you get it right.
I had the same experience as that. I was building a model to like predict MMA fights, and every time you would have a heavyweight, it would always predict a knockout because the percentage is so high. It just figured, hey, if I just predict knockout every single time, I'm likely to get it right.
Yeah.
Nice.
But
Yeah, no, this stuff like this is a balancing act, and it's really important that you understand why it's getting the results that it is.
Yeah, you want to show the ROC stuff you worked on?
Yeah, so the way that I kind of figured this out, how to make it a little more accurate, was I did this thing called receiving operating characteristic. So basically, what this does is it says so this x here would be like the false positive rate, and this y here would be the true positive rate. Okay, so if we were to randomly guess, it would just be a linear equation here. Right? So it's better than a random guess, but it's not very good. But essentially what this does is it takes, so for example, this threshold, and it takes those weights of that threshold, and it tries to figure out, okay, if it's above this threshold, and I have like my score, my confidence, and I move that threshold around, can I get a better false positive rate or true positive rate, right? So essentially what you do is you take this false positive rate and you find where that false positive rate or true positive rate is the highest. So you basically take TPR minus FPR on all of them and you get the highest value. So in this case, the threshold like 0.98, right? So you take this threshold and then you essentially, and to ensure that this score is actually good, you do an AUC score. I forget what this is called. To be
Area under
honest.
the curve.
Oh yes, the sort of, it's just the sort of area under the curve. So if I were to draw out this ROC line here, I was going to go to the board. If I were to draw out this line here, it'd be the area under this curve that you draw here, right? So then so base is 1. If it's 0, then it's just about the same as random choice. And then you basically, so now I pick this threshold. I choose 98 because that's what the best threshold was, or the furthest from random guess. And then I just create this thing called get class. If scores greater than the threshold, you get the Y prediction threshold. And then essentially you create this Y pred threshold that's just, if it's greater than what we said, then it goes, and it basically resets, and you get a much better model. Does that make sense? And I think the reason this score has to be so high is because all the weight is going to that right side and very little weight is going in the actual middle. But what it has in the actual middle is working. Does that make sense? So that's a very common feature of overfitting. You can run an ROC score and it gets a good score and you can figure out where that threshold is. Just if you guys have if it took weeks to train a model and you don't want to retrain it, you can do this. You can do, this took like 7 hours to train. So, but yeah, yeah. I mean, so do you want to talk about the code? Go
Yeah.
through it a little bit.
So
Here you can.
yeah. So for the implementation of transfer learning, so you're good.
There you go. Go for it.
Yeah. So there's a pretty predefined sort of like pipeline you kind of have to go through, and most of it is data. So I'll walk you guys through it a bit quickly. So first, you define the transformations you want to do on the data. So what this does is, this is image pre-processing before the network, and PyTorch has a thing where you can just input a list of the transforms. So what we're doing here is just resizing it to 305 by 430 pixels, transform it to a PyTorch tensor, and then since we're using ImageNet, these values, these hard-coded constants, are ImageNet means and standard deviations. We're normalizing it because we're using the ImageNet weights for the transfer learning. And so then we create the data sets by specifying the folders. And
Oh wait, can you go show them the folder structure really quick?
yeah, is it loaded in this one?
Oh, it might not be actually. Oh.
Yeah.
Okay, but you can kind of show them from there. So.
Yeah. So the root data directory is just where everything's going to be, and then you just have it split into the train, the valid, and the test. And in each of these folders, it's just the images. It's just the straight up images. So yeah, you want to split your image data up into the train, valid, and testing directories.
Oh wait, no, I thought you.
I'm
so I thought
sorry.
you also had the class
Sorry,
directories. You're good.
I lied. This is really hard to do without
Wait,
visualization.
let's just go here.
Yeah.
Let's go show them the files here.
There we go. There we go. Thank you, pal.
Yeah.
So yeah, you have like the test directory, and then you have the classes. So you have the adenocarcinoma images under the test/adenocarcinoma. The normal images under test/normal. And this is like a pretty intuitive directory structure for your images, where you have it split between train, valid, and test, and then you store each corresponding image in the corresponding class directory. And when you do this, PyTorch and TensorFlow kind of take care of making the sort of image dataset object for you. So yeah, once you have something that looks like this in your like directory or where your notebook is, it should work out of the box.
Yeah, so basically you can take anything that's in folders like this, throw it in a thing, change where that folder is pointing to, and you can literally just go through this and train it yourself on whatever data set you want.
Yep. And actually that's what we did, right? Because
Yeah.
first we did adenocarcinoma on CT scans, and then we did pneumonia or normal on X-ray images. So we have something that has like test and then pneumonia and normal. So that's really why transfer learning is so useful. Okay, so I define transformation, and then I create the data sets. So this is just going through everything in the train folder, getting the class, because what this does is it gets the last thing in the file path, which is the label, and then append it to classes, and then I append all the train image paths, and then I do the same thing for validation and testing. And these are this is just a utility dictionary that tells you, if which index corresponds to which label, since we're going to use it's going to predict a number rather than the label itself, so we want to correspond that number to a label. And then we create a dataset class that takes the images and has the initialize, the length, and then the get item functions. Yeah, so what I think what's most important here is the get item. Basically, it loads the image from the file path, gets the label, applies the transforms, and then I'm returning the image object, and then the label, and then the file path itself. But yeah, this is like the basic way of doing transfer learning within PyTorch, or image classification in general. And then I create the data sets by specifying the parameters. And then I create the data loader. This is a PyTorch thing, but you load in the data set object, and then the batch size, and then you have the data loader, which is what PyTorch uses for training. And so here's just an example of an image, and as you can see, here's the file path, here's the dimensions of the feature batch it's in, and then its label, which is 3, which corresponds to adenocarcinoma.
Yeah, so this is the output from Resident, right?
Not yet.
No, not okay.
Not yet.
Never mind.
And so now we're training the model, and so this is going to take a lot to explain. This custom training loop, basically, it's from this tutorial provided by PyTorch, but basically, as you can see, what it does, it loops through the number of epochs, and then each epoch has a training and a validation phase, and it gets the loss and the things that has correct. And then this is what we use for transfer learning for the most part. What this is doing, this zero grad, is saying you're not going to train on the parameter weights. And I think, yeah, you need that to ensure that the base layer is frozen.
And the base layer being ResNet. So
Yeah, the base
so
layer
it doesn't
being
go back
ResNet.
into ResNet and change the
Change
parameters
the
that they
load
have
weights.
trained on.
So,
those images.
yeah, the training function is a bit complex, and there's a tutorial for it, but I'll go into the specific transfer learning part, which is actually really easy. So here, this is, you instantiate the model, you just call a function, and you say that it's pre-trained. And so yeah, we're loading in the ResNet 50 model, architecture and weights. And then you define the number of features being inputted into your custom classifier head. And then you define the last layer, which is your custom classifier head. That's a linear layer with the expected number of features and n class outputs. In this case, with the CT scan, n equals 4, because we have squamous cell, carcinoma large cell, carcinoma, adenocarcinoma, and normal. And then you put it onto a GPU or a CPU. Define the loss function.
Don't use a CPU.
Yeah, this is using a GPU.
Yeah, don't. That's actually not an option. If you use a CPU for this, don't.
Yeah, it's just really if you don't have a GPU.
Yeah.
But yeah, and then we define the optimizer to use for this transfer learning, as well as the scheduler that basically changes the learning rate as you train. And then this is the training loop. We train it for 25 epochs, and as you can see,
How long it took?
no, it doesn't.
That's tough.
Oh wait, no, it does.
Oh yeah.
It took 4 minutes or 5 minutes.
Yeah,
with
but
the
that's with a
GPU.
GPU. With a
Yeah.
CPU, it'll probably almost 10 or 20x
Yeah.
on a loop. So
But yeah, this, I want to emphasize that this cell is the basic transfer learning part. And it corresponds pretty well with what we did, like what the diagram is. You load in the base model and say that it's pre-trained. You specify the next layer, which is this linear layer, to have the number of features that is coming out of this base model. And then you specify the number of outputs that it's going to have for your task. So yeah, in 3 lines of code, you've done basic transfer learning. And yeah, that's the whole training loop for transfer learning. This is just a bunch of stuff that we did on our end for
yeah.
keeping track of like the accuracies and the confusion matrices. But yeah.
Yeah.
Any questions?
Probably
Right,
lost some
awesome.
of the code. But yeah, I mean, that's pretty much all I mean, other than, I guess, oh, close. Okay, does it still have this? Yeah, okay, so now you can see what the results are on the testing set, actually. So this one here, I don't know why it's doing that, but, I mean, it's normal anyways, so you can see it's kind of weighting normal things, like on the outside-ish, inside-ish. Yeah, you can see I picked and choose which one to use for my presentation. You get roasted. This is the one I probably ended up choosing. Yeah, and then large cell. I honestly don't know what these things are. If anybody knows, can. No, okay, sick. We'll just believe, because it came out really well. But yeah, I mean, this one's probably. I mean, that's a weird looking heart. I'm not gonna lie. But yeah, essentially, this is what the results are, and you can come down here, or well, yeah, and then you can, on the actual notebook itself, you can go to the links, and you can go and look through them yourself on the notebook. And we basically did the same thing here. We just replaced the folder names up here, and I actually so we had a very small validation set for this one. So I basically just like switched which folder it was at the beginning. Still works, it's fine. But just FYI, because I didn't want to have to like go through and change all the val to test. I was just like, whatever. But yeah, I mean, that's pretty much it. Guys, have any questions? Just let me know. Yeah. Sweet. Any questions? Yes.
When deciding which metric you want to use between the accuracy and the F1 thing you were talking about, what do you want to take into consideration when you choose which one you want to look at as like best metric for how to verify your model?
Well, we trained ours, so a metric is just like explaining how performant the actual model is. So the most important thing, so a metric is kind of like saying over time how well it's doing, whereas like a loss, so we actually chose a categorical cross entropy loss, right? Yeah, which basically just tells you, how do I explain this?
So basically, like, it's used for multi-class classification.
Yeah, it's specifically for multi-class classification, and typically when you're doing something like this, there's going to be like some sort of predefined loss for your. So like there's like certain types of machine learning. There's like classification. There's like segmentation. There's natural language processing, and typically all these different types of machine learning have one specified loss that is like standard throughout like the research papers on that one type of learning. So like for example, like in segmentation, something that's like a loss function that we would use is a sort of is called an IOU, or like an intersection over the union. So the main difference between this and the other one is that in segmentation, you're basically defining a class for each pixel. So instead of having like, it's like a cross entropy for each pixel instead of a cross entropy for the entire pictures class.
Yeah, and to extend off of that, it's really like domain and task specific.
Yeah.
You know, if you have 1.2 million images of 1,000 classes, but you have an equal number of images in those, there's not much imbalance. But in the nature of medicine, right, as Jim pointed out, it's very common to have imbalanced data. So that's why accuracy may not be the best fit. And so when you consider the problem space you're working in, or even just what data set you're working with, like that's why Kyle did the ROC rather than just looking at accuracy. That's to fix the problem of imbalanced data sets somewhat. So yeah, there's a lot of different metrics you can use for measuring the performance of a machine learning model, but yeah, it varies across domain and across tasks. So yeah, just keep it in mind.
Hopefully that answers your question.
Yeah,
that answers.
Which context you're working within.
But the real answer is, if you want a metric, just add the metric, because it won't change anything. So just after every step, just add like say an F1 score, if you want to see how the F1 score is performing over time.
What exactly is an F1 score?
Jim.
Okay, so I think to truly explain this, I kind of need to like draw a diagram of the computer matrix. Okay, so can you raise your hand if you think you fully understand what a computer matrix is? Okay, so let's explain like.
Oh yeah. This is a confusion matrix.
Yeah.
Wait, Jim's. Yeah. Can you just point it towards him? No.
Okay, so when we have like a prediction, it can either be like correct or incorrect. And let's say that we're classifying things as like positive or negative. And so here, I'll say this is positive, this is negative, this is positive, and negative. So one of these axes is going to be the predicted label, and one of these axes is going to be the true label. And so let's just say you can do either order, but it's important you're clear on which axes is a predicted versus true label. So like, let's say this is the prediction. And let's say this is the actual. And then let's say that we have 1,000 examples. So we have 4 boxes in our grid here, and they need to add up to 1,000. And the idea here is, let's go cell by cell. So the first cell is where it's predicted to be positive, and it actually is positive. And let's say that there's like 800, or like let's say 700 of these. And let's say that if when the actual is a negative class, but it predicts a positive class, let's say this happens 50 times. When the actual is positive but predicts negative, let's say this is like 100 times. And then they need to add up to 1,000. So 700 plus 50 is 750. 750 plus 100 is 850. This needs to be 150. Okay, so there's a variety of different metrics you can use. Does anyone know what the accuracy of this model is? So the accuracy is the number, it's like the ratio that it got correct. So which ones are correct?
850 or 1,000.
Yeah, exactly. So the correct ones are here and here. So add up the correct values and divide by the total count. And so this is 700 plus 150 over 1,000, which is about, yeah, as mentioned, 85%. So this is the accuracy. If you want to compute the F1 score, you need to compute 2 metrics known as precision and recall. And maybe how you can like pull up a formula. It's basically like the sum of a ratio computed from this vertical and this horizontal. It's like a ratio of true positives versus false negatives, sort of thing.
Should I just look up F1 score?
Yeah, sure. Look at precision and recall too. Yeah, that's perfect. Okay, so precision is number of true positives over the number of true positive plus false positives. So true positive is when it's actually positive and you predicted positive. A false positive is when it's actually negative but you still predicted positive. And so those are represented by these 2 cells here. So what is what's precision here? True positive is 700. Right. True positive is 700. This doesn't work.
You have like 1 minute.
Okay.
Just by FYI.
700 plus 50. So the precision, this is the value. Maybe you can put that in the calculator too.
Yeah.
That's the precision.
$93.33.
93.33.
Yeah.
And for the recall,
0.4. Oh, sorry.
Recall's 0.4?
Yeah, I think exactly.
Okay, so the recall is
actually no, it's 150 over 250.
Yeah. So it's 150 over.
Is that right?
Wait, really?
True positive?
True positive over true positive.
Oh wait,
is
no,
false
no,
negative.
never mind.
So true positive and a false negative is when it's actually positive, which predicts negative. So that's why it's called a false positive versus negative. It's a false positive if you predict positive, but it's not. So it's positive, like you say it's positive, but that's false. That's why it's called a false positive. And same for false negative. Here, this is a false negative. And so recall we consider here and here, right? The number of true positives over true positives plus false negatives is 700 over 700 plus 100. So this is recall. And what is this value?
0.875.
0.87. Okay, 87.5.
Yeah.
And then for the F1 score, we just need to take
2 times precision times recall over precision plus recall.
Right. Okay. So this is a concept known as a harmonic mean. It's a mathematical thing, and you can look more into it if you're interested. But we'll just use a formula for now. And so 2 times precision times recall over precision plus recall is, I think there's like a lot of numbers you can put in the calculator.
Yeah.
Like
So
2 times, precision, 93.33 times recall, which is 87.5 over, is it precision plus recall?
Over precision plus recall, yeah.
Yes, okay. So 93.33 plus 87.5. Okay.
0.903.
Okay.
Two.
this F1 score. Yeah, 0.9032. Okay, so these are just like a couple of metrics that you can use. If you want to understand it really well, I would recommend like working on an example for yourself of confusion matrix. But like these are metrics that are very often used in practice. And of course you can use like as many metrics as you want, right? The most popular accuracy, recall, precision, F1 score, and then there's the RLC curve, area under the RLC curve, and intersection over union. These are the main like metrics used. I encourage you to like look into them if you're interested in like evaluating your model's performance from a very objective standpoint at a variety of angles. Yeah, that's an example, a probably worked out example of F1 score.
Nice.
Hope that's clear.
Thank you, Jim. That was impromptu. We did not plan that. All right. I think that's it. Thank you guys for watching.
Yep.
Thank you guys for joining. Appreciate it. Have a good one, guys.
Thank you.
Yes.